Hello everyone. In this particular lecture, we are going to see the concept of a CRO, signal generator, power supply, and multimeter. So these equipment we required in our lab to test some circuits, to give supply to some circuits, to measure the parameters inside the circuits. So let's start with the CRO. So in study of CRO, the aim of this particular experiment is to study CRO, that is cathode ray oscilloscope, to study front panel of CRO, use of CRO to measure amplitude and frequency. It may be a square wave, a triangular wave, or a sine wave. We can measure the amplitude and frequency of all these signals. What we required in this case, we required apparatus, that is CRO, cathode ray oscilloscope, and we require probes for connection from external world or from external equipment. Panel of CRO. This is CRO that is given by a company called Applab. It is a 20 megahertz dual trace oscilloscope. So dual trace means there will be two traces. So one trace, the dedicated part for this is called channel Y, and this is the dedicated far part for channel X. So by using this we can have one trace, and by using this we can have a second trace. So you can see here there are several buttons available, or we can say knobs available. That knobs is used to control the parameter that we are going to measure, or we can say amplitude, frequency. So in this case, you can see here a red LED is there and a red button is there. So this button is on off button. This LED will glow when we press this switch to make it on, and when we release this switch, it will become this CRO off. This is the knob that is dedicated for intensity and focus. So we can adjust the intensity of the CRO using this knob, and we can adjust focus of this CRO using this knob. So this is called as a rotation. So where if the signal over here, if get tilted like this, we can adjust the rotation from this knob to get the signal in a straight line. You can see here, this is the knob that is used to change the vertical distance. We can say this distance. So this knob is used to place that particular signal at horizontal at x-axis, and then this knob is used to make the vertical changes. So similarly, this is for channel actually Y, and this is for channel X. So we can say these two are, we can say, the twins. One can handle channel Y and one can handle channel X. So above which, this is the button that is dedicated for time scale. So we can increase the time or we can decrease the time using this time based knob, or that is called also time scale knob. So this is the variation knob for the horizontal variation. We can vary the signal in horizontal direction. We can place the signal at center, and we can vary the signal in horizontal direction. While these two knobs, they are used for the vertical deflection. This is the knob. This is called as a level knob. This will stabilize our this signal, and this is a variable knob that is used to, if level is not working at some frequencies, this knob will be useful to adjust the frequency, or we can say adjust the signal on this particular screen. So these are the knobs, several knobs available, several functions available. They can be used to have various functions. We are not going in detail of each and every functions. This connection is used to provide signal to external world, while this for channel Y and this for channel X to provide signal to this CRO. So this will be act as an input, while in this case this will be act as a external. We can say that will be output to external world. So this is regarding this front panel of the CRO. So you can see this is again the simulated front panel of the CRO. You can see here rotation knob, intensity knob, focus knob, on off knob. Then you can see here the channel X and channel Y in here. So this is channel X, this is channel Y, channel 1 and channel 2. can call it them as uh, this is for the position. We can adjust the position vertically. This is for channel Y, position vertically. This is a voltage per division knob. This will adjust the voltage per division of these signals. This is also voltage per division. We can say vertical deflections, and this is for the x direction deflection, or we can say horizontal deflection. This is the trigger pin where we can have a level hold off, that will be going to get adjusted. So this signal will be adjusted and then we can do the measurement. So this is again for the external world, and this is for channel Y, and this is for channel X. This is the pin that is used for the ground. So we can have a test point in here so that it will be act as a ground. So how to measure the amplitude or voltage on a CRO? It is very simple. So for that purpose, we need to understand that we need to measure the vertical divisions. We can say the number of vertical divisions. Okay, so we can see here 1, 2, 3, here is 4, 5 and 6. So there are 6 number of divisions in there. And what is the value of the voltage per division? So both voltage per divisions knob at 0.1. So we suppose that the channel Y is connected. So division voltage per division knob is at 0.1. So we can see here it is at 0.1 voltage per division. So what we can say from that? So 6 division multiply by 0.1 voltage per division. This division will get cancelled. So it becomes a 0.6 volt, or we can say 600 millivolt. So this is the way we can measure the voltage or amplitude of the signal, but that signal's amplitude is peak to peak voltage. What is it? It is a peak to peak voltage. So we can say peak to peak voltage measurement, it is equal to number of vertical division multiplied by volt per division. So here there are 6 division vertically and the knob is at 0.1. So 0.1 volt per division. If we cancel division, we have 600 millivolt. Now if we want to measure only the peak, if we want to measure only the peak, so what will be the formula? That is equal to VPP divided by 2. So you know peak to peak is nothing but 2 VP. So that's why we can say VPP divided by 2. So 300 millivolt will be the peak voltage. And what is RMS voltage? So peak voltage VP divided by root 2. This is called as a RMS voltage. So 212.13, according to this formula, it will be the RMS voltage. So if you measure the peak to peak voltage by using this vertical divisions and voltage per division knob, if you multiply them, you get V peak to peak, and from that you can calculate VP, that is V peak or peak voltage, and then RMS voltage. So this is the way we can measure the amplitude and voltage on a CR. So how to measure the frequency, or we can say how to measure the frequency on the CRO. So in this case, the frequency measurement is very simple. So for that purpose, you should know what is called as crest and what is called as trough. As you know, if you see the sine signal, these part are called as crest and this part are called as trough. Okay, so you know that the number of horizontal division from or between two crest or two trough, they are called as a lambda, called as a wavelength. So if we calculate wavelength in division, it will be in a division. You can calculate from this to this place 1 2 3 4 and 5. So you can see it is not actually 5, it is 4.6 division. So this is a wavelength called as a lambda. Then you are going to find out the time division knob, because we are going to measure the frequency, we need a time division knob. So time based knob is needed. So time based knob is 0.1 millisecond per division. So we can calculate capital T, that is called as a period. So capital T period is nothing but lambda into T, small t. So 4.6 division into 0.1 millisecond per division, that is equal to 0.46, and it is in millisecond. So if we take the frequency, to calculate frequency, it is nothing but 1 upon period, 1 upon T. So 1 upon 0.46 millisecond is nothing but 2.17 kilohertz. So the frequency of this signal is 2.17 kilohertz. So how it is calculated? So it is calculated like measure the distance between two crest, or measure the distance between two trough, that is considered to be as lambda. Then you can take a time based knob, where is that knob is situated, and you multiply that by t. So lambda into t is called as capital T. So capital T will come in millisecond, because the division will get cancelled. We'll have a reading in a millisecond. So we are getting a time period. So f upon 1 up, f is equal to 1 upon t, it will give frequency. You can see here, this is a frequency measurement on CRO. So for that purpose, what we need number of division on x-axis called as lambda. Then we are going to find out the value of t by observing the time based knob. Then we can calculate t is equal to lambda into t. We can calculate finally f is equal to 1 upon t. So we can do it for 5 times, so that we'll have a observation table of the CRO. See, in case of observation table for amplitude or voltage measurement on CRO, so we have to find out the number of division on y-axis, and then we have to find out voltage per division knob reading, and then by multiplying them both, division will get cancelled. So this will be in a division, while this will be in a volt per division. Division will get cancelled. We'll have a reading that is in. So we can calculate peak to peak. Then we can have V peak by divided by 2. Then we can have V RMS by dividing this VP by square root of 2. Okay, so we can have another table for it as well. So we can have 5 readings, so then we can complete this observation table of amplitude or voltage measurement on CRO. So let's look what we are doing in the lab. Right. You can see this is a AppLab CRO 30 megahertz dual trace oscilloscope. We'll have on off button here, intensity, trace, focus. So this trace is nothing but a rotation button. Here is a test point. Then this is X Y channel actually, and this is actually X channel. You can see here time per base knob, level button to adjust the signal. This is a hold off, hold on button to make the signal hold on and off. This is for the horizontal direction, and this is for the vertical direction. You can see there are several functions available. This is also the functions available for vertical direction. Channel Y, we can insert in here signal from external world. Channel X, we can insert in here signal X, and this is for the external world. So look at here. So this is a probe, test probe we have in our lab. So I am inserting it in channel Y, making the CRO off by pressing the on button. Look at here, you can see something on the CRO. So there is a line. I'm going to test the probe first. So testing the probe is very simple. Just connect it to the positive part of this probe and connect it to this test point. You can look at here. Here I am wearing the voltage per division knob, and there is a waveform that is called as a square waveform. You can see here. So this is the test waveform, and then by adjusting the time based knob, I can adjust the frequency, and by adjusting the voltage per division, I can add frequency. So by level button, I can place them at x-axis, and by variable button, I can place them so that we can start from this and ends towards this for the amplitude and voltage measure. So look at here how to measure the amplitude of this signal. So I am going to measure the vertical distance. Vertical distance is actually 2. So you can see here, this is these are the two divisions, and here you can see this is connected at a 0.1 volt per division. So 2 multiplied by 0.1 volt per division, this division and this division, 2's division will get cancelled, so we'll have 0.2 volt. So the signal, this signal has an amplitude of 0.2 volt. So how to measure it? It is very simple. Look at it again, where we can calculate a frequency from this signal. You can see here, this is the starting point of the square wave, this is the ending point. So you can see here the divisions 1 2 3 4, and approximately 5 divisions are there. So lambda is equal to 5 division. And what is t? So small t is equal to, it is very near to 0.2, so 0.2 millisecond. You can find out capital T from it, so lambda into small t. So you can have a t is equal to 0.2 millisecond into 5. So I have already cancelled the division, so that t is nothing but 1 millisecond. So if I take the frequency of it, 1 upon t, 1 upon 1 millisecond, that will be equal to 1 kilohertz. So By this way, by using this time based knob, the wavelength lambda, you can calculate a frequency. So this is the way to calculate amplitude and frequency in case of a CRO, cathode ray oscillator. What we need an apparatus called CRO, signal generator, and probes. So we have seen a CRO and probes. We need to study first of all signal generator, and then we are going to combine CRO signal generator together with the probes to find out how to measure the frequency and how to measure amplitude, as well as how to generate the frequency and how to generate the amplitude. So this is a front panel of the signal generator. You can see here, this is AppLab, made by company AppLab, 3 megahertz multi waveform signal generator. This is the model name. You can see here, this is a frequency and VPP button. We can select this button to have a frequency or have a voltage over here. So these are the frequency range starting from point like 0.1 hertz or 0.2 hertz towards the megahertz, that is 3 megahertz. You can see here, this is the frequency variation knobs coarse. It will uh, vary the frequency majority portion, and fine will do the fine adjustment. This is the symmetry button that we don't have use in here now this time. This is hold on button or offset button. These are the functions. We can have a sine, we can have a triangular, and we can have a square. So these are the three buttons to change the functions of the signal generator. This is the level button, and this level button is nothing but, in case of this signal generator, this is a voltage or amplitude button. So this button will change the voltage or amplitude of the waveform, while the frequency will be changed by using frequency range and coarse and fine. So this is the TTL output, where we are going to get a 5-volt output constant with different frequency. Okay, so we are going to get square waveform from this particular uh, TTL output, while in this particular we can say output will get a functions. Functions may be sine, triangular, square, with different voltage and different frequency. 1 megahertz multi waveform signal generator. You can see, by pressing this button we can change from voltage to frequency. See here, so it is now a frequency. Previously if I pressed it, it was a voltage. So now you can see here, these are the frequency ranges starting from 0.1 hertz to 1 megahertz. If I press 1 megahertz, it will show to the megahertz, while if I press the lesser button, lesser signal, or we can say the range, it is very less, then we'll have very less frequency. So you can see here, if I press the 1, we'll have 1.323 hertz. So it will if I press again the other button, it will show the different frequency. So this is due to the coarse and fine. So if I make the coarse very small, very less, we can say approximately equal to 0. And if I press some sort of switch called, suppose I press 1k, you can see here, so minimum it shows 32 hertz, and if I really increase it to the further, means at the maximum, it will go towards the 1.3. So I press 1k, it was showing 1.3 hertz. So whenever we are adjusting the frequency, what we should do, we should keep the fine button. You can see here, this kept fine button at the center position, and then we can do the adjustment using a coarse button. So if I supposed want to adjust 1 kilohertz frequency, then I am going to put it at the center, and then by using the coarse sign I will go to the nearest value, and then using fine button I can select the particular frequency. Then this is the different waveform. You can see here, if I press the triangular, it becomes a triangular waveform. If I press square, it becomes square. If I press sine, it becomes a sine. So offset is always kept at off position, and the symmetry is also at off position, means at minimum side. We don't require, while we are using these three functions with different frequencies and different wavelengths. So you can see here, while doing the voltage adjustment, I have to press the VPP, then I have make the knob to 0, and I have pressed the 20 and 40 knob together. So 20 and 40 knob, what will do, it will give us a maximum value of 0.2. Now if I release a 20, so what it will do, it will give us a minimum value 0.02, while the maximum it will give a value called 0.2. If I press the 20, release 40, it will give us a minimum value 0.2 and maximum value 2 volt. And if I release both, So it will show us maximum value called 20 and minimum value 2. So whenever we want to select the particular voltage, we want to select this combination of 20 and 40. And if I have to adjust to 10, I have to release both this. Then I am going to adjust towards the nearest value. So if I have to adjust suppose 5 volt, then I am going to adjust using this label button to approximately 5 volt or accurate 5 volt. So for that purpose, what we need to adjust level in a such a way that very cautiously we have to adjust so it becomes a 5 volt. So now this function generator, what will have, this function generator will create 5 volt and frequency of 1 kilohertz. So this is the way we can have amplitude and a frequency. So look at here, we have to change the frequency, then we can press the other button using coarse and fine. We have to keep the fine button at middle, and using coarse and fine button we can adjust the frequency called 10 kilo. So now the voltage is 5, right? The voltage is 5 and I am adjusting the frequency towards the 10 kilohertz. So this particular AppLab function generator, it response is very slow. So we have to change the knob and wait for the result to be get stable. So you can see here 10 I have adjusted, so now it is 4.99. I'm adjusting it to 5. So in this way we can have 10 kilohertz and 5 volt. If you have to adjust the voltages, suppose 0.25 volt or minimum of which I'm going to adjust by using this two buttons called 20 and 40. So this is the way I can adjust the voltage and adjust the frequency using this particular AppLab 1 megahertz multi waveform signal generator. You can see here this is signal generator and this is CRO. So we are going to connect the signal generator with the CRO. So for that purpose, what we required a probe that should be connected at channel Y. So I have done it. Then I required a probe that should be connected at the function terminal or function pin of this signal generator. I'm going to connect the positive with the positive of this function generator, and then the negative wire should be connected to the negative of this signal generator. So you can see here some waveform is shown on this particular CRO. We have to adjust it by using voltage per division, and we have to adjust the time scale time now by using time per. You can see here sine waveforms are shown in here. So we have to adjust so that we can at least see two crest or two trough to measure the actual frequency and measure the voltage. So we have to adjust in a such a way that this crest should be adjusted at one some part, and then the next part will be available in here. We can measure the distance between these two, and using time based knob we can calculate the frequency. Similarly, it is adjusted in a such a way that so that it will calculate us the vertical directions, so that vertical divisions with this voltage per division knob, as we have seen previously, we can calculate the voltage using these two things. So by varying the voltage per division knob, according to your adjustment you can adjust it so that we can measure the voltage per division knob. It will show us the same result. It is kept at 1 or kept at 0.2 or kept at 0.5. It will show us the same result, but it should approximately acquire the 70% of the screen with two crest or two trough, and with the amplitude of at least 70% of the screen, then we can do it. So you can see here by using this knob, you can see here I have adjusted it to 2 volt and a frequency of 1 kilohertz. Actually you can see here 10 kilohertz. It's actually a 10 kilohertz. This frequency is of 10 kilohertz and this amplitude of 2 volt. So if we measure it using this particular knob and this particular knob, vertical and horizontal direction, we will get the same result. So if I make the function change to a triangular, then for triangular as well as lambda is same 2 point, then time per base, multiply it by them, calculate t, and then f is equal to 1 upon t, and same divisions time per base. Same in case of a square, we have to start from this part and ends on this part for the calculation of lambda. Then we can calculate time base frequency and then voltage per division vertical direction. So you can see here, if I change the frequency, the time base knob is going to get adjusted according to our frequency on the signal generator. So I am making the frequency very small. You can see the effect on a CRO. So it is same for the sine as well, as square was showing. This is actually for the sine. If I minimize the waveform and if I maximize the waveform, if the maximize is done, so we have to adjust the time per base knob so that we'll have two or two crest or two trough at least. Okay. So we are not going to make this waveform for the calculation. We have to make at least two crest or two trough. This is the horizontal direction button. So you can see here, this is a triangular waveform where we can have the variation in frequency as well as variation in the amplitude. So we have to adjust at each point. When the frequency get more, we have to adjust the time per base knob. When the frequency is less, we have to adjust the time per base knob. When amplitude is more, we have to adjust the time voltage per division knob. If the amplitude is less, we have to adjust the time per base knob. So these are the basic thing that we required. So you can see a square waveform, we can adjust the amplitude by using this level button on signal generator, and according to which we can adjust the voltage per division knob. In this way we can adjust the, if it is out of the screen, we can adjust it to in the screen. If it is very